In this session we will talk about optical fibres. Before we do that, we're going to just revise what we know already about refraction. So here we have air and glass. We've got a ray of light, a ray of red light travelling across from the air, across the boundary into glass. Now the refractive index here of air is 1. The refractive index of glass is 1.5. Let's just remind ourselves what we mean by the refractive index. The refractive index n of a substance is the speed of light in a vacuum divided by the speed of light in that substance. Now the speed of light in air is pretty much the same as it is in a vacuum, 3 times 10 to the 8 meters per second. So if these are the same, we work out the refractive index of air, it is 1. But the light will slow down as it crosses into the glass because it's got a much higher refractive index. So if we think about it here, the speed of light in the glass, if we rearrange this formula, will be the speed of light in a vacuum divided by the refractive index of the glass. Speed of light in a vacuum then, 3 times 10 to the 8 meters per second. If we divide that by the refractive index of glass here for red light, what we will end up with is 2 times 10 to the 8 meters per second. So what will happen here as the ray of light passes across the boundary from air into glass, its speed will slow from 3 times 10 to the 8 meters per second to 2 times 10 to the 8 meters per second. The result of that then is that the ray of light will be refracted as it reaches this boundary, and it will be refracted towards the normal. So here is our normal line. A normal line is always drawn at 90 degrees to the boundary. And what will happen is the ray of light will be refracted out of the air into the glass, and it will be refracted towards the normal. So it will bend around this way. We can always imagine that or work that out by imagining the light consisting as a series of wavefronts. Here are the wavefronts here. Basically this side of the wavefront hits the glass first, slows down. This side of the wavefront here is still travelling at full speed, and that means it's going to get skewed around. This side is going to sort of overtake this side, and it's going to end up bending this way, like that. Now we can calculate the angle of refraction using Snell's law. So if we call this angle here theta 1, the angle of incidence theta 1, and we call this angle here theta 2. Let's suppose for our particular ray of light here, so if the angle of incidence theta 1 is 50 degrees, we can use Snell's law. N1 sine theta 1 is N2 sine theta 2. So we have, and therefore rearranging, so sine theta 2 is 0.51. If we inverse sine that, we'll get the angle theta 2, and we come up with 31 degrees. What about if we have the other possibility, the other situation, where instead of having our ray of light moving from air into glass, it moves from glass to air? Well, this time we can see that the ray of light will be bent away from the normal. Again, if you imagine the light being made up of wavefronts here, this side of the wavefront will hit the air first and will speed up. This side is still travelling slowly in the glass, so this side of the wavefront will overtake this side. Okay, this side here will overtake this one because it's moving faster in the air, and that's going to bend the light away from the normal. So if it's refracted out of the glass, it will be refracted like that. However, whether or not refraction actually occurs will depend on this angle of incidence here that we can call theta 1. If that angle is small enough, then it will be refracted out. But as we increase this angle, of course, the angle of refraction will increase. Now, the biggest angle of refraction we can get is at 90 degrees. What you'll tend to find at large angles of incidence, as well as having a refracted ray, you'll start to see some of the ray of light being reflected as well. Okay, so as well as having that refracted ray, we will start to get some light being reflected at this boundary. Now then, what will happen, we will reach a point here at the critical angle where the angle of refraction is actually 90 degrees. So at the critical angle, what's happening is our ray of light is actually being refracted out, but with an angle of refraction of 90 degrees. Now at that point, we're also going to get a significant amount of the ray being reflected. So that's occurring at the critical angle, and we can work out what that critical angle will be for this boundary, because again, using Snell's law, n1 sine theta 1 equals n2 sine theta 2. We're going this time from glass towards air. So we're starting in the glass, refractive index 1.5. At the critical angle, if the angle of incidence here is the critical angle, moving out towards the air, the angle of refraction is 90 degrees. Now sine of 90 is 1, so the whole of that right hand side becomes 1. And we've got 1.5 sine critical angle. So the sine of the critical angle here is just 1 over the refractive index of the glass. So sine theta c equals 0.67, and therefore the critical angle will be 41.8 degrees. That means any angles greater than 41.8 degrees, we won't get any refraction at all. All of the ray of light will be reflected. So at 42 degrees, 43 degrees, and any angle in fact bigger than 41.8 degrees, you won't have any refracted ray, you'll just have a reflected ray where the angle of reflection equals the angle of incidence. Okay, an optical fibre makes use of total internal reflection. So we've just seen here for an air glass boundary or a glass air boundary that the critical angle was 41.8 degrees. So remember, for total internal reflection, two things must be true. First, the ray of light must be travelling towards a boundary with a material that has a lower refractive index. And secondly, the ray of light must be incident on that boundary at an angle that is greater than the critical angle. Now that is what's going to happen here in our optical fibre. So the glass here, the glass fibre, has got a higher refractive index than the air outside it. So when a ray of light enters this fibre here, if it strikes this boundary, provided it's hitting that boundary so that the angle of incidence there, measured to a normal at that boundary, provided that angle of incidence is greater than the critical angle, our ray of light will be reflected. It'll be totally internally reflected instead of being refracted out of the fibre. And the idea with our optical fibre then is that this ray of light will constantly here be being reflected. Each time, angle of reflection will match the angle of incidence. Provided that angle of incidence is greater than the critical angle, what we're going to get each time is reflection until our ray of light exits the fibre. Each time the angle of incidence must match the angle of reflection. And there we go. We're transferring a ray of light there through the fibre. And that's very useful in communications because optical fibres are used to transfer digital communications. So generally what you would be doing is transferring pulses of light waves. So basically it's a digital signal, so you're getting a series of ones and zeros. So if you imagine the intensity, going that way against time going to the right, what you have basically, that's intensity of the light wave. You've got a pulse there, that corresponds to a 1, another pulse, and if there's no pulse, that's a 0. Another pulse, and basically he's sending these pulses representing either an on or an off signal. He's sending those down the fibre to the other end, and that's how optical fibres are used in communications. However, when we use a step index optical fibre, rather than just having the glass air boundary, we put a cladding on here. So let's have a look at that. Okay, so here we have our step index optical fibre, where you can see here we've got a core and we've got the cladding here between the air. So the core of the fibre is surrounded by this cladding, which again has got a slightly lower refractive index. So remember, if the ray of light here is going to be refracted still at this boundary, sorry, if it's going to be reflected at this boundary, then we need the cladding to have a lower refractive index. So this first point here, the ray of light must be travelling towards a boundary with a material of a lower refractive index. So the cladding has to have a lower refractive index than the core, otherwise the ray of light would be refracted out, it wouldn't be reflected. But if you notice here, the refractive index of the cladding is only usually a little bit less than the refractive index of the core. It's not the big difference that you would have with air. So let's just have a look. What difference is that going to make to the critical angle? So let's calculate the critical angle again now of this refractive index with the cladding in place. So write out Snell's law. Again, we're going from the core to the cladding here. The boundary we're looking at is the core cladding boundary. So the refractive index of the core is 1.5. Angle of incidence is the critical angle. Of course, if we're calculating the critical angle, the angle of refraction will be 90 degrees. We're looking at that limiting case between the ray being refracted out and being reflected back. Now when we do that, then we come out with the critical angle of 75.2 degrees. So this time our angle of incidence has to be much greater if we want our ray of light to be refracted. Now you might think, well, that's not as good surely, because what that means, if we have a ray of light, let's say at 50 degrees, if that angle there was 50 degrees, that ray of light, of course, whereas before it would have been reflected down the fibre, it's now going to be refracted out of the fibre here into the cladding, and we're going to lose it. In order to be reflected, the angle of incidence is going to have to be much greater than it was before. It's going to have to be at least 75.2 degrees. However, actually, that is an advantage because it stops something called multipath dispersion. One problem you've got with optical fibres is you've obviously had a ray of light travelling basically straight down the axis of the fibre, which is just about possible here. That ray of light would take less time to travel through the fibre than one that was constantly being reflected backwards and forwards all the way down through the fibre. I'm not going to draw it all the way down, it'll take me too long, but you get the idea. A ray of light that's constantly being reflected from one side to the other like that would take much longer to travel through this fibre than one that was travelling along the axis. So this non-axial ray here taking a long time to travel through the fibre, travelling backwards and forwards with lots of reflections, much longer than this one, and therefore if we take our original pulse that would look like this, what that will do is it will broaden that pulse, so these pulses would then be much broader. I've drawn that very well. And what they would do is they would end up overlapping, which obviously we don't want. We're not going to be able to detect the ones and zeros like we did before. So we don't want that, what we would call multipath dispersion. Now obviously here then, if we can increase the size of the critical angle, what that would mean is now that ray of light there would be lost. It would be refracted out of the fibre. And the only rays of light that we would allow through would either be the axial rays or ones that are travelling nearly along the axis, so that they're being refracted because they're travelling much closer, travelling along this axis here. So that is one advantage there of putting the core in. Yes, we're still getting total internal reflection. That's still possible because the cladding has still got a refractive index that is lower than the core, but we're stopping those rays of light which are travelling back with lots and lots of reflections, which are going to take much longer to travel through. The ray of light now has got to be travelling much closer to the axis of the core in order to be reflected backwards and forwards all the way down the fibre, and we're therefore limiting multipath dispersion. So if we list all of the advantages provided by the cladding, first of all, as we've seen, it's got a lower refractive index than the core, and that ensures that total internal reflection can take place. But also it increases that critical angle, and that will reduce the amount of multipath dispersion, since any rays of light with just a very small angle of incidence are going to be refracted out of the fibre, and therefore the only rays that obviously travel through the fibre are going to ones be the axial rays or the near axial rays that are all going to take similar amounts of time to pass along the fibre. Now there are other advantages to the cladding as well. So it prevents the core from becoming scratched. It stops the fibre becoming damaged basically, which could lead to light leaving the core. Let's just explain that for a moment. Imagine we didn't have the core and that enabled then the core to become scratched. What would happen there? Well, if you imagine having our optical fibre here like that, and we've got our ray of light travelling down this core through total internal reflection. Now for each of these reflections, of course, the angle of incidence will equal the angle of reflection, but we're only going to get total internal reflection if this angle of incidence is above the critical angle. Now what effect might that have if this fibre becomes scratched at this point? So if we scratch or chip this fibre here at that point there, we've got damage to the surface of the fibre. How is that going to affect this ray of light if it's incident on the surface of the core at that point. Well, you can see now what's going to happen. This ray of light really is going to be incident on this core now at an angle that is less than the critical angle. And so instead of being reflected as it was before, it's now just going to pass out of the core here. And so we're going to lose that fibre. So having a cladding there now, if we've got the cladding in place and we scratch the cladding, it's not going to make any difference to the ray of light. You're scratching it on the outside of the cladding, that's fine. But if we obviously don't have damage to the core, and the ray of light then is incident at that point, it's going to be a good chance that that's going to lead to refraction out of the core, and we're going to lose more of our light, and we're going to have less light transmitted through the fibre. Now, another thing to appreciate is that optical fibres are usually arranged in bundles. So if you're using them for communication, you wouldn't just have one optical fibre, you'd have them arranged in a bundle so that you could send lots of information down the optical fibres in different cores. And therefore, it is important to have the cladding there so that you keep the core of one fibre away from adjacent fibre cores, because otherwise, if the cores could touch, then you could have a signal crossing over from one fibre core to another, what we would call crossover or sometimes crosstalk. So we're preventing that. Obviously, very important that we prevent that from happening, and the cladding is what does that. And finally, the cladding provides tensile strength to the fibre, and that really helps to prevent it from breaking. Now, we can understand that if we realise that the core of these fibres is actually really thin. I mean, the way I've drawn it there, it looks like it's quite thick, but it's actually in practice really, really thin. Because if the core of the fibre is thick, then what that means is there are lots of different paths the ray of light could take through from one end of this fibre to the next. So you've got more chance of these paths where you've got lots and lots of reflections up and down the fibres, lots of different paths that it can take. And if it can take many different paths, all at slightly different angles, while still being reflected along the fibre, that's going to produce pulse broadening, which again, obviously, we want to avoid that. So it comes down to this preventing this sort of multipath dispersion again. To prevent that, we want the fibre to be as thin as possible, but of course if they're really thin, they're going to be prone to snapping and breaking. Adding the cladding will provide tensile strength there to that fibre and help prevent that from happening. Of course, another advantage of having the fibre as thin as possible is that we can get more fibres in a bundle, and that means if we've got more channels then of communication, we can transmit more information. So that's another reason we want the fibre to be thin. Okay, it's helping to stop this sort of multipath dispersion, but also it means we can get more fibres in a bundle. We can therefore have more data down our cables. Finally, when using an optical fibre, one thing we ought to appreciate is that we really want to be using monochromatic light. Okay, so monochromatic light is sent down the optical fibre to send digital signals down optical fibres. What does that mean? Monochromatic means single wavelength, so single colour, single wavelength. And the reason for that is that the refractive index in the core of blue and red light, different wavelengths of light, will be slightly different. For example, blue light has got a higher refractive index than red. Now remember, if it's got a higher refractive index, that's because it's travelling slower in that material. So if blue light travels slower than red light, even if it's taking the same path through the fibre, it's going to take longer to reach the end of the fibre. And what we will get is pulse broadening due to spectral dispersion. So instead of receiving a nice clean pulse like that, so that pulse would be broadened because we'd get the red light received first and the blue light then will be received sometime later. So we get broadening of our pulse. Instead of having a nice clean pulse like that, we get something like that. As we've mentioned before, one key use of optical fibres is in communications. And compared to transmitting signals through copper cables, optical fibres have a number of key advantages, and we ought to be aware of what those are. Well, one is that light has got a high frequency, and that means the signal can carry more information. And that's important, for example, for enabling things like high-speed internet. We need to be able to transfer lots of information. We can, as we know at the moment, they're putting in optical fibre communications in most towns and cities through the UK to enable this high-speed internet connections. The high frequency of light transmitted through optical fibres carry a lot of information, enables that to happen. The other thing, of course, we know that electrical signals produce resistance heating. It causes heating in the wires, and that obviously produces energy losses. We don't get that problem here in optical communications. The light doesn't heat up the fibre. And finally, no electrical interference is going to happen with optical fibres as might happen with copper cabling. One other use of optical fibres that we should be aware of is their use in endoscopes in medicine. So basically in an endoscope, light is transmitted into the body through one optical fibre and then returns through another optical fibre. So you have a bundle of fibres. Light is transmitted through some and then transmitted back through others, and that enables doctors to see down inside the body, and that enables them to improve medical diagnosis. So there we go. Optical fibres can be used to see inside the body, and that is their application in endoscopes and enables improved medical diagnosis.